Okay, so previous lecture we looked at how you find the value of your compensation cap for dominant pole compensation. So we'll continue with that, and we'll just consider one more example. So let's assume your C out equal to 10 picofarad and I load equal to 0. When I say I load equal to 0, this means R load equal to infinite. Okay. So if I draw I'll just simplify the diagram. So first stage I can draw like this. So I'll call it RO1, CO1. This is grounded plus minus. And then second stage you have this power FET. And now I'll consider the beta factor. Okay. So the loop I broke at feedback point. So this will be your V out and this will become your V in for loop gain analysis. This is your VDD. So for a small signal that will be ground. R1, R2, which is 10 picofarad. Correct. What was the value of CO1? Anybody remember? 4.6 picofarad or 6.5 4. And this was I think 500k. Correct. Now let's assume this is 50k and this is also 50k. Okay, so you can choose VREF accordingly to get the whatever V out you want. Okay, or if your VREF is fixed, then you have to change the feedback ratio. So I'm just assuming beta is half. So 50k and 5 on 1.5 volt output. The same example, then your VREF should be 0.75. Okay. So now what is omega P2? Sorry. This was RO2, I think. RO2 and CO2. So omega P2 equal to, what was the value? 300 kiloradian. So one thing you need to remember, if you change the load or which is changing your output resistance, this omega P2 will not get affected, only the output pole will get affected. So omega P3 is what? 1 over. So how much is that? What is the R out here? sorry, I think this is wrong, huh? Your output cap should be here. Correct? So 1 over 100k. How much? That is 10 pico. How much is that? Hmm? 1 mega radian. Okay, so now you have both the poles. We need to find the gain. Okay, do you remember the size of this? W by L was 72,000. Correct? So find the GM. R out is known. So what is the GM for this?
40,000.
It was 40,000, not 72. Okay. So what was the formula for GM? Or if I call it M3, and this is GM1.
For the current of 10 milliamp, we are calculating.
Not 10 milliamp. Now what is the current? Your load is load current is 0. Huh? So what is the current here? V out divided by 100k. So 1.5 divided by 100k, 15 microamp. Huh? So what do you need to know first? Calculate the GM. VGS minus VTH. Huh? So what is that for 10 micro? You know the size. You know the ID. Find the VGS minus VTH. So VGS minus VTH will be very small for this because your current is very low and device size is very large. Okay. Now how much is that? Divide by 50. 3.87 millivolt. It's pretty close to 0. Huh? So that is VGS minus VTH. Huh?
GM value
Okay, so what is the GM?
7.7
7 point?
7.
So GM is 7.7 milliampere per volt. Okay. And what is your R out?
Amount is 100
No, but there is a one more R out in parallel. Huh?
RDS.
Yeah. So what is that?
Lambda we can
1 over lambda. Okay, so this is the smallest device. So assume lambda equal to 1. The channel length was 0.18. So RO3 equal to 1 over lambda ID equal to 1 over 15 micro. So this comes 6. Okay, parallel with 100K.
$40.11.
40. So our out is 100K parallel with so GM into R out. So the gain of your output stage, let's say I call it A3, is GM3 into R out 40 into 3.87.
40 into 7.7.
Oh, sorry. 40 into 7.7. So kilo and milli is cancelled out. How much is that? 30.
8.
And the gain of your first stage? A2. A2 equal to GM1 into RO2. What was the GM1? We calculated yesterday. 50 micro or something? 50, huh? 50 micro multiplied by 500K. How much is that? 25, huh?
Yes.
So first stage gain is low and output stage gain is higher because the device is GM is very large and R out is also I mean you can say it's a kilo ohm, so obviously it's not that small. And if you calculate the same output stage gain at 10 milliamp, you will see that will drop actually because your R out will be, even the GM will increase a lot at 10 milliamp because proportional to square root of your current. But since R out is inversely proportional to ID and GM is square root, so it's a square root inversely proportional to square root basically your gain. So gain will drop. So if it, let's say 100 times you increase the load, so your gain might drop by 10 times or so.
Calculating omega P3, why didn't we include this the output resistance of the MOSFET in time?
Why? Because that at that node you have a 2 resistance, huh?
No, but it is 100K and won't it be parallel to?
Yes, so that is parallel with your RDS of your transistor, huh?
Yeah.
So that's what we did, huh? 100K parallel with 66.7K.
So that while calculating the gain, we assume then while calculating omega P3 that C out into R out. So at that time.
Oh, you are saying the. Oh, sorry. No, your R out 40K, huh? That's correct. What is the problem?
Not here, sir. At the
Your output-
It's omega while calculating the frequency.
No.
Talking about
Frequency, you are talking about the gain or frequency?
Frequency.
Omega P3.
So in the omega P3, you have to look at the effective resistance at this, this node,
Yes, sir.
which is your V out.
Still,
No.
when you're taking capacitor as source, that resistance RDS will be parallel to
100K, yeah. So
So So,
So-
in calculation of omega p3 also we should take 40k only.
Yeah, we have to take 40k, correct?
But there we took 100k
100K.
in omega p3.
Oh, you are saying this one, huh? Yeah, correct. So this should be 40k. So it will be 2.5, huh? 2.5 mega radian, correct? So now your gain is, overall gain is obviously not small, it's pretty large actually. 25 multiplied by 7700. So it's how much?
dB it is
Close to 70 dB or what?
77.7.
77, closer to 80 dB. And if you calculate at 10 milli or so, it may drop to maybe by 20 dB or so. So 57 dB. And I think we assume 60 dB. That was a rough assumption, but it will be less than that actually. Okay, but it does not matter. You should know, like, whatever the gain, you have to start from there, and where the pole is occurring, based on that you calculate the UGP. So now I'll roughly assume 80 dB gain, so that it will simplify the calculation. Okay, so your A naught is 7700, which is 77 dB. I will approximate it to 80 dB. Okay. If you consider the beta factor, then what will be that? It will further drop by 6 dB. Huh? So beta I naught, let's not do this in that case. Beta I naught is 77 divided by 2, which is close to 70 dB now. Okay. So now if I draw the loop gain, you start with 70 dB. So where is the first pole? 300. And your second pole, where was that? So pretty close to 1 decade away from this, huh? You can see. So this is your omega P2, this is your omega P3. Now your drop will happen at, so this is minus 20 dB per decade, this is minus 40 dB per decade. So when you hit the second pole, your gain will be, I can say, close to 50 dB. Because it's almost 1 decade away. So 70 dB minus 20 dB.
Or 50.
Now you have to, with minus 40 dB per decade, you have to drop 50 dB. So how much frequency I have to travel from there? Can you tell? 25 mega is 40 dB. So slightly above 25 mega you can say. So I would assume 30 mega also. Okay. So let's say 0 dB. And here 30 mega. So what will be the phase here? Again, phase margin is very low, huh? Because by the time you hit, so here when you hit the second pole, your phase will already drop by 90 degrees. Okay, now second pole again almost a decade away from here, so that will also cause 90 degree phase shift. So your phase margin is almost zero here.
Proceed.
So again unstable. So what do I do? If I have to compensate it, shall I add the capacitor at output or at omega P2?
Capacitor. If you're adding capacitor at omega P2, it will push omega P2 towards left and
Omega P3 we will require very fast.
Yeah, so we talked about this yesterday. Huh? You will require at very large cap, because when you compensate at the output, so your worst case will be the maximum load. Correct? Because at the maximum load your R out will be very low, so you'll require a very large cap to make it dominant. But if you put the cap at omega P2, your worst case is the lightest load, because at the lightest load your output pole will be at lower frequency. So if your dominant pole is at omega P2, you know as you increase the load, your second pole will be pushing at higher frequency. So it will further improve your phase margin. So if you compensate at a lightest load by putting the compensation cap at omega P2, then for higher load it will be automatically compensated, because you know that second pole will be moving at higher frequency. And that's what you want. Huh? You want to move your non-dominant pole outside your UGB. Okay. So now compensate by adding CC at omega P2. So again consider 60 degree phase margin. So phase margin equal to 60 degrees. So what should be the pole frequency? So omega UGB should be how much? Omega P3 divided by 1.7. Omega P3 is known, 2.5 mega over 1.7. How much is this?
so 1.443 mega radian per
1.44 mega radian per second. Then omega P3, sorry, omega P2 compensated. What should be this?
omega UGB by DC gain.
Okay, 1.44 over
DC gain. Our
DC gain is beta A naught, which is roughly 70 dB. And 70 dB is how much? 3500?
3000.
Okay, so divided by, how much is that? Let me just write the final number. 400. Okay, omega P2 is known, 1 over again RO2 CO2 plus CC, which should be 400. So we need to find CO2 plus CC equal to 1 over 500K multiplied by 4. So this becomes 1 over 2 multiplied by 1, 2, 3, 4, 7, 8. Five nanofarad. Hmm? Again, CO2 is very large compared to nanofarad, so we can ignore. So CC is approximately 5. So 5 nanofarad is very large cap again. I mean, it's almost impossible to put on chip. You can put, but then all the area will be occupied by your capacitor compared to your circuit areas. Okay, 90% area will be taken by your capacitor. So, which is not preferable. So, which means if you want to do the dominant pole compensation, you will again require very large cap, whether you put at the second stage or first stage. It may not. Obviously, at the second stage, it will require even larger, which is only possible with the external cap, like order of microfarad. 5 nanofarad is possible to put on chip, but again, it will take a lot of area. So practically not feasible. We never put order of nanofarads cap on chip unless you are only designing the regulator chip. But most of these regulators are part of a bigger system, and you don't want to bloat the area just by increasing the size of your regulator. So, what do we need to do?
If you attach the capacitor between
So, we require Miller compensation. Okay. So 5 nanofarad is